Okay, 30S Physics. Here are the work practice problems solutions that I'm going to write up for you. Unlike before, I'm going to make just one kind of continuously running video to get through all of these problems. So you might have to scroll ahead to find the specific problem that you're looking for if you don't intend to watch them all. With that said, I'm going to get right into it with number one. So number one says an 80 Newton force has been applied to a block. The block moves 20 meters in the direction of the force over level ground. Question is, how much work has been done to the block? So this is a really straightforward question. We're focused on the applied force and nothing else. So the fact that there's a normal force or a force of gravity or anything like that really has no relevance here, as you'll see right away in my solution. So let's get right into it. Okay, so the applied force, F applied, is given to be 80 newtons. The block moves 20 meters in the direction of the force, so that's the distance moved. D equal to 20 meters. And that little bit about it's going in the direction of the force tells me that that beta angle, beta, is equal to 0 degrees. It's actually moving in the same direction as the applied force. So there's no angle between the direction of the motion and the direction of the applied force. The question is, how much work has been done to the block? Well, there's only one thing that did work, and that one thing is the applied force. So the work done by the applied force is what we're looking for. This is a straightforward application of the equation. The work done by the applied force specifically is equal to the applied force, the distance over which it was applied, which really is that full 20-meter distance, cosine of that beta angle as it pertains to the applied force, which is 0 degrees. So work equal to 80 multiplied by 20 multiplied by the cosine of 0 degrees, which of course is 1, positive 1. So this is going to be an answer that I don't even think I'm going to need a calculator for. 80 times 20 is going to be 1,600, and of course the SI unit of work is the joule. That's it for number one. I'm going to press ahead right into number two. Okay, number two says, calculate the work done when a 20 Newton force pushes a cart 3.5 meters over flat level ground. Basically a repeat of the kind of question that we just did, so let's knock this one off quickly. Calculate the work done. So this is again the work done by some kind of an applied force. That's what I'll call it, even though the question I don't think specifically called it that. 20 newtons is what I'm going to refer to that applied force as. 20 newtons. A distance of 3.5 meters. Beta, again, the question doesn't explicitly say it, but if it's just being pushed across the ground, it's going to move in the same direction that it's being pushed. So beta is equal to 0 degrees. So once again, work applied, force applied, distance over which it was applied, cosine of the beta angle. I guess I'm being a little inconsistent with my use of subscripts here. I could have put them over here for the given values here, but this is such a basic question that I don't think it would have been a problem if I had skipped that. Okay, so work applied equal to a force of 20, a distance of 3.5, and again cosine of 0 degrees, which is positive 1. So 20 times 3.5, again, calculator not yet needed, so I think I can pull that one off as just being 70 newtons. There we go. Pressing ahead. Number three. How much work is required to lift a 360 kilogram piano to a window whose height is 10 meters from the ground? Okay, so presumably this is going to again be applied force. So let's just get right into that there. How much work is needed? Work done by an applied force is unknown. This time we're given a mass of the piano here. So the mass is given as 360 kilograms. We're lifting up to a height of 10 meters, so I'm just going to consider that a straight up distance of 10 meters. We're pushing that piano up. And of course, since it's moving up and being pushed upwards, the beta angle is going to be equal to 0 degrees once again. So a straightforward question, but one extra layer of complexity from the previous questions. If there is this piano, which I'll just represent as a generic box here, while it's being lifted, there will be no ground or, in other words, no normal force that's relevant to the piano. So it would have, oh, that's jumping around on me, sorry. It'll have a downward force of gravity, and it will have this upwards force applied. Okay, now, this is a nuance the first time you come across it, but let's just be clear. In order to lift that piano up, you would need to apply a force ever so slightly greater than the force of gravity at first to get it going from the ground, but truly throughout the lift. Imagine this. Imagine that it's just moving along nice and slowly at a nice constant velocity, constant velocity, constant velocity throughout the lift. That's what I'm really focusing attention on, is while lifting at a constant velocity, which is definitely what I'm assuming. Constant, let me get that in there. Typo. There we go. Constant velocity. The acceleration would be 0, meaning the net force would be 0, meaning that the size, the applied force, would have to match the force of gravity. Yeah, we're not like trying to like rocket launch this piano upwards. We're just lifting it along. Reading into the question, I'm imagining it's happening at a slow and, more importantly, constant velocity. That tells me that the applied force can be calculated in the same way that the gravitational force can be calculated as m times g. With that said, the work done by the applied force is equal to the force applied, the distance over which it's applied, times the cosine of the angle that pertains to the applied force. And then just a quick substitution here. The applied force, as we just talked about, is the same size as the force of gravity. So when I write mg here, I'm not actually referring to the force of gravity. I'm actually still referring to the applied force, but they are equal in size here. The distance over which it is applied times the cosine of beta. Okay, now I'll put my numbers in here. So this is equal to, m was 360. Times the gravitational acceleration or gravitational field strength, either or, 9.8, multiplied by the distance over which we lifted it, which was, I can never remember these things, oh yeah, 10 meters, and cos of 0 yet again, which is positive 1. Okay, so grabbing a calculator because I'm not quite that good on this one, so 360 multiplied by 9.8 times 10, I'm not even going to punch in cos of 0 because I know that one is positive 1. I get an answer on my calculator of 35,280. I'm just going to record that to 3 significant figures. That's getting annoying. I'm just going to record that to 3 significant figures of 35,000. And again, calculator says 280 at this point. I'm going to round that off to 300, and of course the unit of joule. And for those of you who aren't aware of it, my preference for final answers, unless I have a good reason to do otherwise, is 3 significant figures. So that's why I'm rounding it off this way. The 353 are significant, those zeros are not significant. Okay, now it might be overkill, but let me show you a different way to solve this very same problem. Okay, so we're lifting it up from the ground, presumably, up to a height of 10 meters. Consider the following to be an alternate solution that is equally correct. There's no need for you to do it both ways, but let me just show it to you. Okay, so there's the ground down here. I'm imagining that the piano has started on the ground, but then we're lifting it up to a, let's call this a new height of 10 meters. I'm saying a new height because it started down here at a height of 0. And again, I'm using my prime notation. So the height without the prime, or h without the prime, is the starting height, and the h with the prime is the ending height. Okay, let's try this. The mechanical energy that it ends with is equal to the mechanical energy it started with, plus the net work that was done along the way by any force, gravity excluded. Okay, m prime, k prime plus u gravity prime equal to k that you started with plus the gravitational potential energy you started, plus the net work done by non-conservative forces. Well, there was only one force doing work, and that was the applied force. So I can actually kind of sketch that in here. There is an applied force. There's also force of gravity, just for completion's sake. I won't draw in a normal force because really I'm thinking of it along the way. So just imagine that it's ever so slightly not yet, or having just recently left the ground. So the normal force is not present on our piano. Okay, now, this next bit requires a little bit of an explanation. I'm going to cross out k prime and k. The reason I'm crossing them both out is I'm imagining either one of two situations, both of which are equally valid. Possibility number one, I could think of, they're both equal to 0. The piano was sitting at rest on the ground, and then I lifted it, so it was initially 0. And once it got to a height of 10 meters and I said, that's good enough, that's where I want to put it, I can imagine that I stopped lifting the piano, so its kinetic energy would again be 0. So you can think of both initial and starting kinetic energies as being zero, even though it wouldn't have been zero throughout the motion. Doesn't matter. These are the final and initial values, so we could think of it that way. Another way to visualize this is to imagine that I did kind of just move it along nice and steady, nice and steady, nice and steady, nice and steady. If I want to kind of exclude like that starting and stopping, then I could imagine that K prime and K are not equal to zero, but they're equal to each other. Namely, the speed of the piano did not change, so whatever this K prime was, it was the same as the starting K. So I'm imagining that I've just initialized a movement, so it's moving up at some starting value of kinetic energy, and it continues to maintain that same kinetic energy value throughout the whole lift. So either way you could think of it, the Ks are gone. I can also cross out the potential energy from gravity at the start for the reason that it was at a height of zero at the start of this scenario. What that means is that the gravity, oh, I should go back to my green pen here. So what that means is that the gravitational potential energy that it ends with is equal to the work that was done by the applied force. And that statement alone should make some sense since work is the act of transferring energy. So in lifting it, let's imagine that it was me physically lifting it. I would have been doing work in giving it that height that it's reaching, the potential energy that it has upon getting to a higher location. Okay, finishing this off, mg height prime equal to, and resist the temptation of saying force times distance here, because don't forget that it is very much the work that we're trying to find. The work done by the applied force is the unknown here, so don't sub in a force times distance. That would be counterproductive right now. It's just the work done by the applied force. So the work done by the applied force is equal to mg height prime. The m was 3, well actually just check this out. mg h. Even though before I wrote it in a very different way, hopefully you can see that that 360 is the m, the 9.8 is the g, and that 10 meters can be interpreted as the height prime. So that's going to very much come right back to the same numeric value. M 360, G 9.8, and now I'm thinking of H prime as being that 10. Surprise of surprises, the answer is the same, 35,300. 35,300 joules, again rounded to 3 significant figures. So either one of these is fully correct. You don't have to do it both ways. You can take your pick. Okay, moving along. Number 4. If 100 Newton force is applied at a 30-degree angle, pulling a 15-kilogram block for 5 meters, how much work is done on the block? Okay, so just when you see a question like this, you sometimes have to have a little bit of interpretation here. So there is this object, this 15-kilogram object, so let's just get that in here. M is known to be 15 kilograms. And there's an applied force of 30 degrees pulling it. The 30-degree angle is not described completely, like measured from where, but I think it's a pretty safe interpretation to say that it's being pulled at a 30-degree angle above the horizontal, or more specifically, 30 degrees from the actual motion of this block. Okay, so we're pulling it along at a 30-degree angle with some kind of an applied force. I don't think we're going to need it for this question, but yeah, there's a force of gravity, and yeah, there is a normal force. The question didn't mention anything about friction. It's not really needed for the sake of this question, but lacking more information, I would just assume that there is no friction. Okay, so how much work is done on the block? Again, by the applied force is the, I think, the intent here. So the work done by the applied force is what we're looking for. We know the mass is, yeah, we're not going to need the mass here to tell you the truth. The force applied is 100 newtons. Beta is 30 degrees. And it's going to be pulled a distance of 5 meters. How much work is done on the block by the applied force, again, is my understanding. Okay, so work done by the applied force is equal to force applied, the distance over which it applied that force, cosine of beta as it pertains to the applied force. So this is the 100 newtons, the distance of 5, times the cosine of, 30 degrees. Okay, so the first part there is pretty easy, 500, but I'm going to use a calculator and multiply that by the cos of 30 to find an answer of 433 joules. And that should do it for that one. Okay, moving along. Number 5. Of course, you can hit pause anytime you want to, but I'm going to just chug right along here to get this done. Number 5 says an elevator must lift 1,000 kilograms, a distance of 100 meters at a velocity of 4 meters per second. It's moving upwards, or you could think of that as even as a speed of 4 meters per second. A, how much work does the elevator do? Interpreting that as how much work did the elevator do to that 1,000 kilogram object? And then part B is how much work is done every second by the elevator. It's moving along nice and steady. Okay, so I'm not thinking of the elevator, I'm thinking of whatever's inside that elevator, the mass of 1,000 kilogram. So there is this, there's this object here, this mass of 1,000 kilograms. It's being pushed upwards by the floor of the elevator, which I'm going to think of as a normal force, and of course being pulled down by the force of gravity. So that's not the ground in the usual sense, that's the floor of the elevator. Elevator distance being lifted is 100 meters, and it's not going to be needed here. I haven't looked at these problems ahead of time here, so honestly, I'm thinking here, that speed is not, well, actually, okay, I'll show you an alternative way to solve that in a minute. I don't really need that speed. What I really need to know is that it's not changing. So the acceleration is 0. The net force is 0, so the normal force will certainly match the force of gravity. Otherwise, it would be accelerating. So the velocity of 4 is really not needed here. So MD, yeah. So part A, how much work did the elevator do? So this really is the work done by the normal force. Well, the work done by any force is equal to the size of that force, the distance over which that force pushed. And since the elevator floor is very much moving, it's applying that force over a distance, times the cosine of 0 degrees, because the normal force is upwards, the motion is also upwards, so 0 degrees once again. Okay, the normal force is, as described before, the same size as the force of gravity. I'm just going to sub in an mg, times the distance of the normal, times the cosine of 0 degrees, which is equal to 1,000 times 9.8 times the distance of 100, cosine of 0 degrees. So this really is just 9.8. Actually, I'm just going to do this. Hey, you don't even need a calculator for this one. Check this out. That's just 9.8, and then it's being multiplied by 1,000, but also being multiplied by 100. So that's really just 10 to the power of 3 plus 2, 5 joules. So 9.8 times 10 to the 5 joules should be it for that one. That was part A. There is a part B that says how much work is done every second by the elevator. Okay, well, you could just think of it this way. For part B, if we're only considering a timing of 1 second, here's where that velocity is going to be needed. 4 meters per second, right? So it was moving along at I'm just going to think of it as a speed of 4 meters per second. Yep. So it's pretty clear that the distance that it'll move in that 1 second is equal to v times t, which is equal to, I'm just going to say it, 4 meters. Not the answer to the problem, that's important though. So if we only consider that amount of lift, I can repeat part A in effect, but only looking at that smaller distance. So we're not looking at that whole lift of 100 meters, we're only looking at this very, very tiny lift. So the work done by the normal force is going to be equal to normal force, the distance over which the normal force pushed, which in part B we're only considering that 4 meters, cosine of 0 degrees. So that's equal to, again, I'm just going to put it 1,000 times 9.8, that's the force. The distance of 4 meters, cosine of 0 degrees, which is positive 1. So in this case, we're going to have effectively, sorry, my voice is getting a bit raspy, 4,000 times 9.8. So 39,200 joules. All right, so that's it for part B. I was thinking earlier of an alternate solution based on power, but honestly, I think I'm going to save that for a later worksheet. So I'm going to press ahead. There's nothing wrong with this solution. Okay, so pressing ahead. Number 6. Determine the kinetic energy of a 500 kilogram roller coaster car that's moving with a speed of 20 meters per second. And then there's a part A, part B. Part A is if the roller coaster were moving with twice that speed. Okay, so actually, again, I really haven't looked at these problems ahead of time. I'm kind of thinking this as a part A, B, C, even though it's not labeled that way, because there is a question even before we get into part A. So I'll just leave it as an unlabeled part here, but before part A, we have a bit of a calculation on our hands here. Yeah, because this question is determine the kinetic energy. That's skipping around. K is what we're looking for, the kinetic energy. It has a mass of 500 kilograms, and it's moving with a speed of 20 meters per second in this kind of question that precedes part A. So if you want the kinetic energy based on that information, it's simple enough, 1/2 mv squared. So that's 1/2 the mass of the 500, the speed of 20, which we don't forget to square. By the way, it's a good habit to do things like that, even in your mind, if you're working on problems on your own. I always emphasize those squares and square roots so that I literally don't forget to do them, because I find that to be a very, very, very common mistake. People just, it just disappears in their writing from one line to the next. I'll just simulate that for you. Imagine that if I just had it like that. A lot of people just make that mistake. It just vanishes. Then they punch in the numbers as you see them without that square. They get the wrong answer and they wonder what went wrong. So when I see things like a square here, I often emphasize it for my own benefit. So 1/2 mv squared, 0.5, 520, I don't forget the square. And then I grab my calculator. So 0.5 times 500 times 20, and I don't forget that square. So I'm getting an answer of 100,000 joules. Yeah, so 100,000 joules, I'll just record that as 1 times 10 to the 5 joules. Okay, so that's number 6, preceding part A, if you will. Okay, part A then goes on to specifically call out, if the roller coaster moving with twice the speed that we were just considering, then what would be its new kinetic energy? Okay, so there's a kind of a brute force way of doing this, and then there's a kind of a faster shortcut way of doing it, especially since the numbers are so nice. There's nothing stopping you from saying, well, the speed used to be 20, so I'm now going to double that and say 40. In fact, why don't I just do that? The speed is 40 meters per second. We're basically looking for an update. What's the kinetic energy based on that? By all means, you can do the equation, you can sub the values in, you can punch those numbers into your calculator again, and you can get an answer, and if you do that without making a mistake, you'll be fine. But these numbers are just begging to be done somewhat more intuitively. Check this out. Since, in fact, I'll write it on here. Since the kinetic energy is 1/2 mv squared and the mass did not change, it follows that the kinetic energy depends on the speed value squared. So as long as the mass is not changing on you, if a speed change occurs, a kinetic energy change will occur, not of the same proportion, but of that proportion squared. So if you double the speed, in fact, let's just write it this way. I'm gonna have to shut that off for next time. I know why it's jumping around, but I'll just live with it for this time. Okay, so since the speed doubled, at least for part A compared to the previous part, the kinetic energy will increase by a factor of, and how about if I just do this for emphasis, times 2, the kinetic energy will change by that same factor squared, since it's proportional to the square. In other words, 4. So since we had 1 times 10 to the 5, it's going to be quadruple that. So the kinetic energy, I'll go back to blue, the kinetic energy is now 4 times what it used to be. It used to be 1 times 10 to the 5. So that means it's now at 4 times 10 to the 5 joules. Okay, now you might be saying, well, you didn't really save any time by doing that. Actually, consider this. What if this was a university physics course and this was a multiple choice question? And by the way, yes, there are occasionally questions like that. If you're doing such an exam, or even an AP exam, although I know this is the 30S course, if it's a multiple choice exam and nobody's even seen what you're doing, if you could take even a little shortcut that you know and trust and feel confident with, you can really, really shave off a lot of time and put that time into other problems, other parts of the exam where you might need that time. So if this was me and not explaining it as I'm going, I literally could have done this calculation in part A. Oh, let me just kind of switch this out. I could have did this answer in part A, and then when the question said, okay, yeah, you double the speed, now what's the kinetic energy? And imagine that's the multiple choice question. Part A, 1 times 10 to the 5. Part B, 2 times 10 to the 5. By the way, a lot of students would pick that one and be wrong. Option C, 4 times 10 to the 5. And then D says, just mark it wrong, I don't know what I'm doing. So if you understand your physics and you understand these proportionality ways of thinking, 4 times the kinetic energy, since you doubled the speed, you'll be that much better off for it. Okay, so completely optional, but I thought I would take advantage of that to talk about it. Okay, I'm going to put that one back. Move on. Oh, there was a part B. Oh, in fact, let's try our shortcut out for part B. Or no, sorry, I thought this was going to change the speed up again. Part B is different. It says how much work would need to be done to the roller coaster car in order to make it move at twice the speed as it had initially. So I'm interpreting that as it was already moving at 20 meters per second. Oh, grab a highlighter. It was already moving at 20 meters per second. What you then do is some work. You do work to increase its speed so that it is then moving at 40 meters per second. In getting from 20 meters per second to 40 meters per second, the question is, how much work would you have to do in order to double the speed the way we've talked about? Okay, so I think that's the gist of the question here. With that in mind, we can go ahead and do this. By the way, if this was a multiple choice kind of a question, I, again, would have known the answer already. I wouldn't even have to write anything on my paper. I guarantee the answer is 3 times 10 to the 5 joules. That's definitely the answer, and I'll explain how I know that to be true in a minute. But let's just kind of show our work clearly, since that's not the case that we're doing a multiple choice question where nobody is seeing my work. Okay, so the question is, geez, doubling. Okay, I'm not liking that. I've turned on my touch screen in addition to the stylus entry, and I'm not liking it. Next time I'm going to keep my touch screen off and only use the stylus, in case you're wondering why it keeps jumping around. Okay, so the question is, how much work would have to be done? I'm really interpreting that as, the net work, because we don't know what is doing this work. So what work would have to be done by non-conservative forces? I think I've usually been using the lowercase there. How much work would have to be doing to move it, or to change it rather, from a speed of 20 meters per second to a new speed of 40 meters per second? How much work would you have to do to double the speed in this way? Okay, well, the mechanical energy this car ends with better be equal to the mechanical energy the car started with, plus any work that was done along the way to change that energy. Mechanical energy is K prime plus U gravity prime, and that's equal to K plus U gravity plus the net work NC. Okay, now, this car is not going up a hill, or for that matter going down a hill, so whatever that ending potential energy from gravity is, it's going to be the same as whatever it started with. So you can cross these out. Again, these both might be 0, or they might both be non-zero but equal to each other, in which case they subtract out. Either way, since this car is not moving vertically, I can cross those both out. Okay, so that means the, there we go. Oh, I hate that. The kinetic energy that it ends with is equal to the kinetic energy it started with plus the net work done by non-conservative forces. That means the net work done by non-conservative forces is K prime minus K. And I already know K prime and K. The net work done by non-conservative forces is K prime. That's what we just calculated in part A. So 4 times 10 to the 5 subtract the kinetic energy it started with, which is what we calculated before part A, the 1 times 10 to the 5. So there we go, 1 times 10 to the 5. So the net work done in order to double its speed this way is 3 times 10 to the 5 joules. And if you recall earlier, I was saying that I intuitively, or I don't know if intuition is the right word for it because I literally thought through the physics of it, I just did it quickly. Work is the act of giving energy. So if it started with 1 times 10 to the 5, and then you wanted to have this much energy, clearly you have to give it energy. Now, how much energy would you have to give it to go from 1 to 4? The answer is 3. And don't let that multiplier throw you off. That wouldn't really affect that fundamental fact. So that's why I basically knew the answers as soon as I got into this one. Okay. Moving on. That was what number here? Number 6? Yes. Moving on to number 7, which I think is the last one, actually. So doing all right here. Number 7 is Lewis climbs up onto a wall that is 3.6 meters high and gains that much potential energy. A, what's the mass? And part B, how much work did he do? Okay, so part A climbs a wall that's 3.6 meters high. I'm going to interpret that this way. I'm going to say that he started on the ground or whatever level it was. I'm just going to declare that to be my starting height. And he achieves a new height of 3.6 meters. Now he gains 2268 joules of potential energy in the process. That makes sense because he would have started with a gravitational potential energy of nothing, so he's going to end up with a gravitational potential energy of 2268 joules, according to the information given. So part A, what is his mass based on this information? Well, you can think of it as, again, conservation of, or actually no, it's kind of overkill really, because we know UG prime. So based on this alone, we can say that the gravitational potential he ends up with is equal to mgh prime. The only thing we don't know here is m, so let's calculate it. M is equal to the U gravity prime over mg, which is equal to 2268 over m of, sorry, what the heck did I do? Clearly this has been a long day for me. Hopefully you caught that before I did, and that was just a goof on my part, and I'm not going to correct it in the video. I'm just going to fix it now. If I'm trying to solve for m, what I really meant to do was take the gravity over mh. So that, sorry, really long day. Let's get rid of that m. There we go. And replace it with an h prime. There we go. Yep. I think that's a good correction there. Hopefully you did catch that before me, and like I said, I'm tired. So 9.8 to continue along here. H prime, which was the 3.6, gives us a value for the mass. Okay, calculator time, 2268 over 9.8, but also over 3.6. So I'm getting 64 point a lot of digits. I'm going to round this off to 3 significant figures. So I'm going to say 64.3 kilograms. Good enough for that one. Now there was a part B. So how much work did he do? Well, in effect, what this person did was transfer energy from their muscles or from, whatever source exactly is not important to us. But they basically transfer that energy into a new form of, in this case, gravitational potential energy. So it's again overkill. Hopefully you know the answer already. The answer is going to be 2268 joules. That is definitely the answer to this question, but I'll just kind of explain it mathematically. The energy he ends with, energy he started with, plus the net work done by non-conservative forces, which really is him, the work done by Lewis in this case. So that means that K prime plus U gravity prime equal to K plus U gravity plus the net work done by Lewis. Okay, I'm going to cross out the kinetic energy prime and K, and the reason I'm going to do that is exactly the same as that piano question that we had earlier on. Think of that lift of the piano as being analogous to the lift of this person. So K prime and K, you can think of them as both 0, or if you imagine a constant speed upwards, then non-zero, but they subtract out in any case. Whoa, that was a crazy zoom in. Okay, cross out the U gravity for the reason that it was 0, and you can see that the result is kind of what I predicted. The gravitational potential energy you end with is the work that was done by non-conservative forces. And there's no calculation needed because this was given in the question. This is the 2268 joules. So 2268 joules, I guess just out of a force of habit, even though this probably is weird, I'll keep my policy of 3 significant figures and call it 2270 just for consistency, if nothing else. And that, oh geez, I thought that was it. One more. Oh, Mr. Dawson, why do you do this to me? Okay, number 8, one more, last one. Tarzan swings from a vine whose length is 12 meters. Tarzan starts at an angle of 30 degrees. I interpret that as the vine was 30 degrees with respect to the vertical, and he's stationary to begin with. So what's the highest speed that he reaches there at the bottom of the arc? And B, how much work did he do? Okay, we'll get to B in a second, I guess, but let's visualize this one. There's a bit more going on in this one. So there's a vine that I'm imagining to be attached at some point to a tree or who knows what, and that that vine rather, initially makes an angle of 30 degrees to the vertical. So 30 degrees. Okay, so this is right here. I'm imagining this to be Tarzan. In fact, I was going to change it to a box, but that's fine. Okay, so we know that the length of this vine is 12 meters. Notice that that is not the height. It's just the length of the vine. He has no speed, so let's kind of write this out here. His speed is initially 0. Yep. His speed is 0, and the question is, what will his speed be at the bottom of the arc? So v prime equal to unknown. Okay, let's be clear here. What's going to happen is when he releases himself from whatever I'm imagining he's standing on a branch or something like that, he's just going to swing down. It'll be actually a circular arc to some point, at which point I really want to know how fast he's going. V prime equal to question mark. Okay, now, to solve this, I'm going to declare, for the sake of this question, that wherever the heck that is, I don't know where it is in terms of where the ground is. He could still be quite high up in the trees for all I know, but I'm going to set that equal to my reference height. So I'm going to say that he ends up at a height of 0. Now the question I have is, so what height did he start from with respect to that reference? Let's just do a quick calculation here to calculate that starting height, because this is going to be found just with a little bit of trigonometry. Okay, so check this out. There's a really nice triangle sitting right here, and it's a really nice triangle because it's a right triangle. I know the length of the hypotenuse is 12 meters, and I know there's a 30-degree angle in there. So how about if we call this value over here, let's call this side of the triangle, I don't know, call it y or something like that. And notice that, again, that y is not the height or anything like that. It's just the length of that side of the triangle. Well, with reference to that 30 degrees, I can see that this is adjacent to it, and there's the hypotenuse. So adjacent and hypotenuse, I'm thinking cosine. So the cos of 30 degrees is adjacent, what I'm calling y, over the hypotenuse, which I know to be 12. That means that the value of y is 12 cos 30 degrees. Okay, so y is, I'm grabbing calculator now, 12 cosine 30, which is 10 point, and this is not the final answer here, this is just a numeric answer that I need to continue the problem, so I'm going to keep a total of 5 significant figures here. So 392 meters. Okay, now how does that help me? Okay, well, you see this vine here. We know that the vine is 12 meters long, but don't forget that this here, connecting down to Tarzan when he's at the bottom of the swing, must also be 12 meters. My diagram probably doesn't show that well, but each of those two segments is 12 meters, the full length of the vine. So what that means is that the height that he started with can be found. In fact, let's just get rid of that exclamation point there. The height that he started with must be equal to the length of the vine minus y. And the length of the vine is known to be 12. That y value, I just found it, 10.392. So, grabbing my calculator, 12 subtract that is 1.6, etc. I'll just kind of write this down in here, h equal to, let's see, 1.607. It's 4 significant figures, so one more, I'll round it to another 7 meters. Okay, so to get the speed at the bottom of the arc, it's important to notice that as he swings down, there are only 2 forces that are acting on him. And those 2 forces, the force of gravity, which is that special force that we don't need to consider in that non-conservative force part, and the tension force, which we can also ignore in this case because it has a 90-degree angle to the direction of motion. And that's true of circular motion, by the way, in general. Any force that pushes towards the center of the circle as an object moves around the circle does no work. 90 degrees between the force and the motion. So what we can do is we can say that in getting down to the bottom, the mechanical energy he ends with will be equal to the mechanical energy he started with, allowing for the possibility that there were non-conservative forces doing work. As just explained, there are no non-conservative forces doing work. Tension force is perpendicular to the motion. Force of gravity is that special kind of force. So, K prime plus U gravity prime equal to K plus U gravity. And the kinetic energy that he started with at the highest point there, he was stationary. At the end, he ends up at this low point of a height of 0, so I'm just going to zero that out as well. Gravitational potential energy is 0 when you're at the height of 0, and your kinetic energy is 0 when you are stationary. So, if we want to know the speed, we can say that 1/2 mv prime squared is equal to mgh. Don't know the mass, and it's not important that we do. Solving for v prime, we can say that's a square root of gh over 0.5. So v prime is equal to the square root of 9.8 times that height that I found over here in green, 1.6077, all of which is over 0.5 inside of the root. So grabbing my calculator, I'm not going to forget that square root right off the hop of the following. 9.8 times 1.6077 divided by 0.5. I'm getting 5.6 rounded to just 1, I guess. So 5.61, excuse me, 5.61 meters per second. And that should about do it for that question. So, oh, part B, sorry, my mistake. How much work did he do? Okay, now, how much work did he do? I'm a little unsure of how to interpret that, to tell you the truth, because the only thing that Tarzan is pushing on is the rope, or pulling on the rope, really. The rope pulls Tarzan, Tarzan pulls the rope. But since he does so perpendicular to the motion, as described before, the tension force is towards the center, Tarzan is pulling on the rope away from the center, I'm just going to say that the answer to part B is none. Tarzan's not doing any work. He's exerting a force on the rope, but that is perpendicular to the motion. So leave it as that. Problem solved, and that's the end. Hope that was of some benefit to you. We'll get you on the next set of solutions coming up soon.